Hey everyone, so in this video we're going to be talking about continuous random variables. So we can let x be a random variable, and if the values x can take on are continuous, then we say x is a continuous random variable. And remember we made the distinction between what discrete means and what continuous means. Discrete is something that's going to be counted, or there are going to be gaps in between the possible values x could take on, whereas continuous is just going to be an interval of values and it can't really be counted. It's more of something that's measured. And in that case, x is going to be a continuous random variable. So the normal distribution, which we talked about in previous videos, is the most famous and most important example by far of a continuous probability distribution. So a probability density function is a function that satisfies the following. So the probability that x is between some numbers a and b is the integral from a to b of this probability density function dx. And if you're not familiar with calculus, that's okay, but all we really need to know here is that this is just the area under the curve between the points a and b. So if this is the distribution of x, our continuous random variable, then the area between this point A and this point B is going to represent the probability that x lies between this interval. So just like when we were talking about PMFs, we do have some properties that need to be satisfied in order for something to be a valid PDF. So the first one here is that f of x needs to be greater than or equal to 0 for all x. And then the second one here is that the integral over x of f of x dx needs to be exactly equal to 1. And this might look pretty familiar to you because remember when we were looking at PMFs, each probability needed to be greater than or equal to 0 for all x. And the sum of each of those probabilities needed to be equal to 1. And if you've taken calculus, which again, if you haven't, it's okay. But if you've taken calculus, then this is just a continuous version of the sum. But what we mean by these is that we're always going to be above the x-axis, which is what f of x being greater than 0 means. And then the total area under this curve is going to be equal to 1. So now let's talk about what I kind of like to call the paradox with continuous probabilities. So we talked about how a PMF gives the probability that x is equal to x for a discrete random variable, but what if we were to ask that question with continuous random variables? So the example that I've used a couple times in the past is the amount of rainfall tomorrow in inches. So what would it mean to ask about the probability that x is exactly equal to 2 inches? Well, in theory, it could rain 2 inches tomorrow, but like I say here, it could also rain 2.1 inches or 1.9 inches or 1.999 inches or 2.234876 inches. What I'm saying is that there are infinitely many values that x could take on. It's an interval of values. So since there are infinitely many values x can take on, technically the probability that it rains exactly 2 inches tomorrow is 0. And this is where the paradox is because it could technically rain 2 inches exactly tomorrow. But since there are infinitely many amounts of rainfall possible tomorrow, the probability that it rains exactly 2 inches is going to be 0. So because of this, we're allowed to say that the probability of x being less than or equal to x is equal to the probability that x is less than x for a continuous random variable x. So in the rainfall example, we could say the probability that x is less than or equal to 2 is the same thing as saying the probability that x is less than 2, because the only difference between these is the probability that x is equal to 2, and that's just 0. So it's so small of a probability that we can consider it negligible. So now let's get back into the normal distribution. And we covered this a couple videos ago, but now it's really time to get deep into what the normal distribution is all about. So remember that the normal distribution is unimodal and symmetric, and it kind of looks like a bell. We actually call it a bell curve. So the normal distribution, if you remember, it has two parameters. It has a mean, mu, and it has a variance, which is sigma squared. And we use this as the notation. So remember when we were talking about the binomial distribution, if x was a binomial random variable, then we would say x follows a binomial distribution with n trials and probability of success p. So in this case, it's pretty much the same thing for the normal distribution. We say x follows a normal distribution with mean mu and variance sigma squared. And we provide this normal distribution with these two parameters because what that does is it gives us a center of the distribution and it gives us a spread. So if we look down here, I got this photo from Wikipedia. We have the various types of normal distributions you can have. There are infinitely many of them. It's a family of distributions. So this first example is this blue curve, and this blue curve is centered at 0. It has a mean of 0, and it has a variance of zero point 0.2, which is a lot smaller than the other variances that are listed here. So since it has a small variance, it's not going to be very spread out. It's going to be very narrow. And this red curve, which is actually arguably the most famous distribution in all of statistics, and we're going to talk about this very shortly, this is a mean of 0, it's centered at 0, and it has a variance of 1. So the variance in this one is higher than the variance in the blue curve, so it's going to be spread out a little bit more. It's going to be not as narrow and tall, it's going to be a little bit wider and flatter. And then the same thing goes with this goldish curve here. It has an even higher variance, so it's going to be flatter and wider than even the red one. And then this green one, it has a variance of 0.5, but the difference here really to note is that it's centered at -2. That's the mean, so that's where it's going to be centered. So based on the parameters that we give it, we can end up with different types of normal distributions. So that very famous distribution that I was talking about a few moments ago is called the standard normal distribution. And this is a normal distribution with a mean of 0 and a variance of 1. We use z to denote a standard normal random variable. So the nice thing about this is that we can take a normal random variable, which we can call x, and we can convert it into a standard normal random variable, which we're going to call z. And the way we do that is by subtracting the mean from x and then dividing by the standard deviation. And this is a process that's called standardizing, which I'm sure is a term you've heard before. And then this last part here is actually very important, and we'll go into it a little bit later. But basically, what z tells us is how many standard deviations away from the mean x is. And like I said, we're going to go into that a little bit later. So standardizing is very important for many reasons, but the main reason is that it allows us to compare values on the same scale. So for example, if I'm in a class that's taking two exams and the exam scores are normally distributed, and I score 76 on the first exam and 79 on the second exam, which exam would you say I did better on? Well, if you don't have any other information, you would say, oh, well, you probably did better on the second exam because 79 is better than 76. And without any information, that's a totally reasonable conclusion to come to. But what if we actually found out what the average scores were? And we found out the first exam had an average of 74 and the second exam had an average of 81. So now when we take a closer look, we'll notice that my score on the first exam was 76, while the average was 74. And then on the second exam, my score was a 79, while the average was 81. So now when we look at it, it actually looks like I did better on the first exam because I was above the average. Whereas on the second exam, even though my raw score was higher, I was under average. So, what standardizing allows us to do is it allows us to put everything on the same scale based on what the mean and the variance are. And we're going to look at some examples of how to do this in a little bit more detail. So, let's look at an example. So, suppose the heights of females are normally distributed with a mean of 65 inches and a variance of 9 inches. So, what's the standardized value for a female at the height of 68 inches? So before we do any of the math here, it's usually helpful to write out the information that's been given to us. So first of all, we need to know what the mean is, and that's going to be 65. And then the variance was given to us, and that's 9. And often when we get the variance, it's usually helpful to convert that straight to a standard deviation because that's often what we need instead of the variance. So when we do that and we take the square root of the variance, we end up with a standard deviation of 3. And then x is going to be this value that we're interested in. So we're interested in knowing the standardized value for a female with a height of 68 inches. So this is what x is going to be. So what we're looking for, again, is the standardized value. And remember, this was z. This is what we called z, our standard normal random variable. So remember that the formula for this is going to be whatever x value is given to us minus its mean divided by its standard deviation. But we already have all of these quantities, so all we need to do is plug them into the formula. So that's going to be 68 minus 65 divided by 3. And that's going to be 3 over 3, which is equal to 1. And remember what z tells us. Z tells us the number of standard deviations above or below the mean x is. So when we come up with a z value of 1, that tells us that 68 inches is one standard deviation above the mean of female heights. So now let's try to get a feel for what's actually going on here when we do this. So remember, our distribution of x was normal, and it had a mean of 65, so it's going to be centered at 65, and then a standard deviation of 3. And remember, when we were talking about the empirical rule, every time we went like one tick mark away, that would be one standard deviation. So one standard deviation above the mean is going to be 68. Two standard deviations above the mean is going to be 71. And the same thing with the other way. One standard deviation below the mean is going to be 62. So what happens when we standardize is first what we're doing is we're taking that value, that x value, which was 68 in this case, and we're subtracting the mean. And what that does is it tells us the distance between the mean and that value. And then we're dividing by the standard deviation. And that'll tell us how many standard deviations away that distance is. So when we convert this to z, this 68 is going to get mapped to this 1. Similarly, if we were to standardize 71, it will come out to be a z value of 2. Or if we were to take this 59 and standardize it, it would come out to be a standardized value of -2. And what we're doing when we standardize is we're putting it on the scale of standard deviations. So immediately what we could do is we could know how many standard deviations away each value is instead of looking at just the raw values. So now going back to the exam score example, let's say we found out that the variance of the first exam was 36 points and the variance of the second exam was 25 points. Now what would the standardized scores be? So let's list the information that was provided to us. So remember the mean score of the first exam, which we're going to call mu1, this is going to be 74. And then we just found out that the variance of the first exam is going to be 36. And if we convert that into a standard deviation, it's going to be 6. And then the mean of the second exam, which we're going to call mu2 for any of the Pokemon fans out there, this is going to be 81. And then the variance of the second exam, we just found out was 25. And if we convert that to a standard deviation, that's going to be 5. So my scores, remember, on the first exam, I got a 76, and on the second exam, I got a 78. And we are trying to determine which exam score was better. So my standardized scores were the following. On the first exam, if we plug that into the formula, we would get 76 minus 74 divided by 6, which would be 2 over 6, which would be 0.33. So on the first exam, I was 0.33 standard deviations above the mean. And on the second exam, my z value, or my standardized score, is going to be 78 minus 81 divided by 5, which is negative 3/5, which is minus 0.6. So I was 0.6 standard deviations below the mean on the second exam. So my standardized score was higher on exam 1 than it was on exam 2. So therefore, it's very justifiable to say that I did better on exam 1 than I did on exam 2. So anyway, that's the end of this video. I hope you found it helpful and enjoyable, and I will see you in the next video. Take care.